For this video, we're going to have the introduction to derivative. So, to give us an intuitive idea of the notion of derivative, let's take a look how it makes sense from the geometric perspective. Exploring the course site, you can find this GeoGebra applet, which I made under the section Miscellaneous. So this applet has its animation turned on, but you can put it off or on as you like. The idea here is to move the slider for h. So as you move to the left, you're actually making the h approach 0. As an effect, you should be able to see that the point Q is getting closer and closer to the point P. Thus, the secant line formed by the points P and Q is getting closer and closer to the tangent line at point P. But more importantly, you should be able to notice that the slope of the secant line is also getting closer and closer to the slope of the tangent line. Now, we would like to obtain the definition of the derivative using limits. We would like to note that the given curve is that of f, and the graph has points P and Q, where P is the point x, f of x, and Q is the point x plus h, f of x plus h. So zooming in the graph, you will notice here that the line colored cyan is going to be our secant line, and this line colored gray is the line tangent to the graph at point P. So since we have lines, so we can talk of its slope. So the slope of the secant line is given by m sub s equals change in y over change in x. So we have f of x plus h minus f of x over x plus h minus x. By simplifying the expression in the denominator, we're going to have f of x plus h minus f of x over h. As described earlier, we would like to make this h to approach 0. So this tells us that the slope of the secant line will approach the slope of the tangent line. So this limiting behavior tells us that the slope of the tangent line can be written as the limit as h approaches 0 of that of the slope of the secant line. So using the expression for the m sub s, we now have the definition using limits of the derivative of the f of x. So the derivative of the function is given by the limit of f of x plus h minus f of x over h as h approaches 0. And this expression is read as f prime of x. And if we compute for the derivative of the function, this is what we call the differentiation. And we call the function differentiable at x equals c if this f prime of c exists. Okay, so for this example, we're going to find for the derivative of the function defined by f of x equals 16x squared. So again, the given is f of x equals 16x squared. So the task is to find for the f prime of x. So we have f prime of x equals the limit of f of x plus h minus f of x over h as h approaches 0. And using the definition of the function f, we're going to have the limit as h approaches 0 of 16x plus h quantity squared minus 16x squared divided by h. So at this point, we can see a square of a binomial. So by expanding this, we eventually get this expression. Also, by distributing 16 over the sum, we're going to get this one. So at this point, we can now remove the 16x squared and the negative 16x squared. Also, observe that h is a common factor to the two terms in the numerator, so we can remove h out of them. So we have h times 32x plus 16h over h. So since h is a common factor, so we can cancel h. So what is left is the limit as h approaches 0 of 32x plus 16h. Now, because h is approaching 0, we are going to expect that 16h is also going to approach 0. Now, since the remaining term does not contain h, so this is the limit of the constant, therefore we're going to have 32x. So therefore, the f prime of x is equal to 32x. Now, depending on what object we are looking at, there are different ways to interpret derivatives. So first, derivative can be interpreted as slope. It is the slope of the line tangent to the curve y equals f of x at a certain value of x. On the other hand, if we are going to look at a function, it is the rate of change of the function with respect to the independent variable. So at x equals c, the f prime of c is precisely the instantaneous rate at which the function is changing with respect to its independent variable at this value of x, which is c. So in this example, we are going to interpret the derivative as a slope. So we are given here of the f of x equals x cubed, and we're going to find for the slope of the line tangent to the curve y equals x cubed at x equals -1. So again, the f prime of x is the limit of f of x plus h minus f of x over h as h approaches 0. So using the definition of the f of x, we will have x plus h quantity cube minus x cubed over h. So expanding the cube of a binomial, we're going to get x cubed plus 3x squared h plus 3xh squared plus h cubed. So take note here that x will have descending powers with exponents from 3 down to 0, while h will have ascending powers with exponents from 0 until 3. And for the coefficients 1, 3, 3, 1, it can be obtained using your Pascal's triangle. Now we can cancel out the negative x cubed and the positive x cubed. And the remaining terms will have h on them, so we can cancel the h. So what is left is the limit as h approaches 0 of 3x squared plus 3xh plus h squared. So now as h approaches 0, so these two terms are going to approach 0 also. So therefore what is left is 3x squared. Now substituting x equals -1, f of -1 will give us 3. So this means that the slope of the line tangent to the curve y equals x cubed at x equals -1 is 3. So next, we are going to find the equation of the line tangent to the curve at the point x equals -1. So since the slope of the line is already available, we may opt to use the point slope formula to find that equation. So at x equals -1, substituting the value of x will give us y equals -1. So we have the point -1, -1. And inputting this in the point slope formula, we are going to have y equals 3x plus 2. Now that we know that the derivative can be interpreted as the slope of the line tangent to the curve y equals f of x, we now have a way to determine if a function is going to be increasing or decreasing. So if a function is differentiable at x equals c, that means the limit that defines the f prime of x at x equals c exists. So we say f is an increasing function at x equals c if the derivative at c is going to be positive. So this graph shows that the function is increasing at x equals c. That is because the f prime of c is positive. And that means that the tangent line at x equals c is a line which is rising to the right. On the other hand, f is decreasing at x equals c if the f prime of c is negative. So in contrast of the graph to the left, you will find here that the tangent line is actually a line which is falling to the right. And because of that, we say that the f is decreasing at x equals c. So for this example, we are given of a profit function. So we have -400x squared plus 6,800x minus 12,000. So at what rate is the profit changing with respect to the level of production of 9,000 units? So please take note that x here is in 1,000 units. Okay, so using the definition of the derivative, so the p prime of x will eventually become -800x plus 6,800. So when the level of production is going to be 9,000 units, and since x is in 1,000 units, so we're going to use x equals 9. So substituting the value x equals 9, so we have the p prime equals -400. So that means that the profit is decreasing when x is equal to 9, where that is the level of production is 9,000 units. So looking at the graph of P, you will notice here that at x equals 9, the tangent line is a line which is falling to the right. So this tells us also that the profit function at x equals 9 is a decreasing function. Now that we have the concept of differentiability, the question is, how are the concepts of differentiability and continuity related? So this result shows the connection. And it says here, if a function is differentiable at x equals c, then it is also continuous at x equals c. In other words, the function being differentiable is sufficient condition for a function to be continuous. And in another sense, we can also say that being a continuous function, it is a necessary condition for a function to be differentiable. So it also means that when f is not continuous, therefore f is also not differentiable at x equals c. And the last statement that I said is actually the contrapositive or the contraposition of this statement. So it is not all the time that whenever you're going to have continuous function, they are also going to be differentiable. And this can be observed in these graphs. So these graphs illustrate functions which are continuous but not differentiable. So the first one that we have here is the graph of the function x to the 1/3 or the cube root of x. So say if we are going to draw a tangent line at this point, we will have this. So it's a tangent line rising to the right. At this point, we can also draw a tangent line, but the line is now a steeper tangent line. So how should a tangent line look like at the origin? It will actually be a vertical line. So we can actually make an observation that as x approaches 0 from the left, the tangent lines are getting steeper and steeper. So in terms of their slopes, we can actually see that the slopes are increasing without bound. So since derivative in the sense of graph is the slope of the tangent line to the graph, and we saw that the definition of a derivative is expressed in limits, so we can say that as x approaches 0, the limit actually is a positive infinity. So the limit that defines the f prime does not exist. That also tells us that the function is also not differentiable at x equals 0. Now for this graph, we have a cusp. So a cusp is defined as a pointed end on which the two parts of the graph meet. So in the graph, we can see a cusp when x is equal to 0. So for this function, f of x equals x to the 2/3. And doing similar investigation just like the first graph, we will observe also non-differentiability at x equals 0. So for the third one, we have the graph of the absolute value function. One good thing about this function is that it can be rewritten as a piecewise defined function. So for x's less than 0, you will have here y equals negative x, and for x greater than 0, you will have y equals x. So in its own right, this function is a continuous function, but the question is it differentiable at x equals 0? So as x approaches 0 from the left, you will actually notice here that the tangent lines will all have the same slope of negative 1. And on the other hand, the tangent lines to the right of 0 will all have slopes which are equal to 1. So if we question about the differentiability of the function at x equals 0, take note that the limit as x approaches 0 from the left is not equal to the limit as x approaches 0 from the right. So the limit which defines the f prime at 0 for the f of x equals the absolute value of x will not exist, precisely because the one-sided limits are not equal. So by looking at the graph, we will see here that we have a sharp point or sharp turn at x equals 0. And for this last graph, we have a similar case. So again, these graphs show us continuous functions but are not differentiable functions. And by saying that, continuity does not imply differentiability.